Hi, my name is SMALLCELLS. I'm with Qualcomm Small Cells Systems Engineering team based in Bridgewater, New Jersey. I would like to give an overview of the Small Cell Forum's P19 front-end control interface. During the writing of the 5G FAPI spec, we have identified a need for an efficient management of the front-end assets by the upper stack. The rich configuration options supported in 5GNR, along with shorter symbol times, necessitated a tight control of the front-end unit, which encompasses the RF, the digital front-end, and the analog beamforming blocks. To address the need for tight coordination between the upper stack and the front-end unit, 5G FAPI specification has taken an approach notably different than its 4G counterpart and introduced the P19 interface. This is a new interface protocol that is dedicated to the control and the configuration of the front-end assets, such as the RF, the digital front-end, and the analog beamforming blocks. P19 document serves as a companion to the 5G FAPI P5 and P7 specifications. Besides enabling the fast dynamic control of the front-end unit, one of the primary goals of P19 is to facilitate network virtualization by allowing stack and front-end unit solutions from different vendors to bind together easily. The concept applies to both the all-in-one small cell solutions, where the upper, the lower layers, and the front-end unit are all co-located, as well as the disaggregated solutions where they may reside at different physical locations. To achieve this, P19 defines a large set of APIs that allow the upper stack to configure the RF, the DFE, and the analog beamforming blocks in a wide range of arrangements, as well as to monitor and adjust their systems parameters at timescales compatible with 5GNR's requirements. Before moving into a detailed overview, it is important to note that the scope of P19 is limited to control path. In other words, P19 does not mandate protocols or interface standards for the data flow between the DFE, RF, or the PHY. I'd like to use this picture to explain the role of P19 in a high-level GNOB diagram. At the top of the picture, we see the upper stack, which includes the L2 and L3 layers. Then comes the L1 layer, which handles the baseband processing such as decoding and the demodulation. And further down, we see the DFE, analog IF, and RF units, and potentially an analog beamforming block. These three blocks, shown in dashed lines, are collectively referred to as front-end unit. It's important to note that front-end unit is a logical abstraction, and its individual physical components can be collocated, such as inside a remote radio unit, or they can be distributed among CU, DU, or RU. The functional demarcation line between the L2, L3, and L1 is also known as the split option number 6. And to bridge the upper stack and L1 layers over this split, the FAPI spec defines two interfaces nicknamed P7 and P5. Here, P7 is dedicated for the data flow, while P5 is used for control plane operations. In this sense, 5G spec mimics its 4G counterpart. What's new to 5G is the P19 interface. This interface gives the L2, L3 layers direct access to the front-end unit blocks for efficient control and configuration. This becomes very handy, especially in dynamic scheduling of the analog beams, where switching operations need to be carried out within microseconds. I'd like to once again underscore the fact that P19 is a control interface, and the data between the upper stack and L2, L3 is handled by the P7 interface, and the data flow between L1 and the front-end unit can be handled by another interface such as ORAN 7.2x. We can summarize the high-level goals of the P19 spec as follows. First of all, it provides an efficient functional interface between the upper stack and the front-end unit to meet the 5GNR's timing requirements. It also allows configuring the front-end assets for a wealth of carrier and numerology combinations. And by prescribing a standardized API, it lowers the barriers in integrating the stack, PHY, and front-end unit solutions from different vendors. How does P19 achieve these high-level goals? It does this by defining APIs in 3 buckets, namely the DFE, the RF, and the analog beamforming blocks. APIs for the DFE and the RF blocks may include functions for configuring the multi-carriers, adjusting gains, the filter parameters, or monitoring the overload sensors, temperature sensors, or measuring the receive or the transmit powers. It's worth mentioning here that it's up to the vendor to declare which of the capabilities that it supports, along with the amount of control it is willing to yield to the stack. APIs for analog beamforming block include functions to copy beam weight tables between the stack and the analog beamforming block. Beamforming table, also known as the codebook, is a repository that stores the complex weights required to form beams in different directions. In addition to the beam weight table functions, P19 also provides hooks to manage the beam characteristics table. This is an optional companion table which stores the physical shape of the beam, which was defined by the beam weight table. The third set of analog beamforming API functions focus on the beam scheduling. Using these functions, the L2 scheduler can request for the analog beamforming block to switch to specific beams at given symbol times within a slot. Here we show a downlink high-level architecture as an example. The picture includes the PHY block on the left-hand side, which handles the baseband processing, the DFE in the middle, and the RF and analog beamforming blocks on the right-hand side. Hierarchically, we break the DFE into 2 as the narrowband and the wideband chains. Within the context of 5GNR, we can think of the narrowband chains as units that process individual component carriers. In this picture, we see multiple downlink component carriers getting combined and further processed by a common wideband chain before getting passed on to the RF chains. P19 API allows controlling of various blocks such as the DFE gains, filters, frequency rotators, resamplers, and DPD blocks. Once again, it's up to the vendor to define and declare the extent of the control given to the stack. In this slide, we're going to take a closer look at the beam weight table. Beam weight table, also known as the beam codebook, defines the phase and gains of individual antenna elements to form beams in specific directions with specific shapes. P19 stores the beam weight table in a matrix structure where each row represents a single beam. In this picture, we assume that the analog beamforming unit has n antenna elements whose amplitude and phases are represented by the complex variable Wij, which is highlighted in the red box. Boxes in green color indicate an antenna element that is used by the beam, while conversely, a gray box indicates an antenna element that is not used by that beam. Beams are not required to use all antenna resources. For instance, beam ID number 4 utilizes only half of the n antenna elements, while beam ID 1 uses all of the antenna resources. By assigning non-overlapping subset of antenna resources, multiple beams can be enabled simultaneously without causing any contention. For instance, beam 4 and beam 7 can be used simultaneously to serve 2 different UEs which may be located in different positions in space. In the case of beam number 1, however, no other beam can be enabled at the same time, as it is leveraging all of the antenna elements. To demonstrate the scheduling flexibility that the beam weight table offers, we look at two sample beamforming scenarios in this slide. On the left side, we see a single beam, namely beam number 1, getting activated. This beam receives and transmits using all available antenna elements. Therefore, no other beam can be enabled along with it. The upside of this beam is, due to the higher number of antennas involved in its synthesis, narrow beams with high EIRPs can be formed. On the right-hand side, we see an alternate scenario where 4 different beams are activated simultaneously. Here, each beam uses non-overlapping antenna elements. This allows simultaneous communication on 4 independent spatial streams. The spatial gains come at the cost of fattening of the beams, however. Compared to the single beam case, beams number 9 to beam number 12 have broader shapes and therefore diminished coverage. Besides the beam weight table, another concept that is supported in P19 is the beam characteristics table. Beam weight table by itself does not store the physical attributes of the beams. This task is handled by the companion beam characteristics table, or BCT in short. BCT characterizes the physical shape of the beam pattern in terms of its orientation in the azimuth and the elevation directions. The figure here depicts a sample beam pattern that is sliced in the azimuth direction. BCT uses several variables to construct a first-order model of each beam pattern. Amongst these variables are peak beam angle in azimuth and elevation directions, 3 dB width of the main lobe, relative side lobe strength, as well as the polarization type. It is important to note that the BCT is an optional representation. If it exists, it's always paired up with a specific beam weight table. The relationship between these two tables can be established in multiple ways, depending on which one originates first. If the beam weight table already exists on the stack, it can be copied to the front-end unit using the API functions provided by P19. The beam radiation pattern then can be characterized through lab measurements, and then the results can be used to construct the beam characteristics table as shown in the red path. Or alternatively, given a desired beam pattern in the beam characteristics table, the beam weights required to generate it can be synthesized using mathematical tools as shown in this path. Actions described here to create the beam weight table and the beam characteristics table can also be carried out on the front-end unit. P19 does not mandate any rules for the generation of the beam weight table and the beam characteristics tables. The boxes shown in dashed lines are all optional units. The P19 API is limited to the exchange of the beam weight table and the beam characteristics table between the stack and the front-end unit. Having said that, this concludes my overview of the P19 spec. I hope you found it useful, and thank you for listening.
And finally, to download the specifications, please visit the Small Cell Forum website. And we're always interested in feedback on the specifications so we can continue to refine and update them.